Hi, this is Guillermo Campitelli, and I'm going to explain concepts of probability theory like events, sum rule, the product rule, using the drone delivery metaphor. Okay, so first the definition of events, but understanding the concept of events, it's more clear if I show you an example. But events are conceptual elements, and they are the elements to which we assign probabilities. So, for example, here event A is the drone landing in an old region. So basically, if the event A would be that the drone lands in any of these areas. So that would be event A. Event B is a drone landing in an inland region. So basically it would be that the drone could land in any of the yellow areas. So this is an event, and we can assign probabilities to those events. Now event C, we can combine events. In this case, event C is the combination of event A and event B. So basically is the joint probability of event A and B. So basically we say event A and event B means that both things have to occur. So event A was drone landing in an old region. Event B was the drone landing on an inland region. So event C is that both things happen. So basically it would be it has to land in an old region, which would be anywhere here, but because event B has to happen as well, it has to be an inland region, so it has to be here. So the probability of event C is much lower than the probability of A and the probability of B, because it's the probability that both of these events happen, not just one or the other. Yeah. Okay, so let's see other concepts related to events. The concept of mutually exclusive events. Two events are mutually exclusive when they cannot be both true. So event A and event B are not mutually exclusive because they can be both true. And we just showed you that if the drone lands here, that would be that both the event A and event B were true. So they both occur. So if they can both be true, it means that they are not mutually exclusive. I'm going to show you examples of mutually exclusive events, but before doing that, this idea of the events not being both true has a name, and it's called a joint probability, and that's what I'm going to explain next. Okay, joint probability, the probability that two or more events all occur. So let's talk about event A and event B again. So event A, it was the probability that, so event A is the drone landing in this old region. Event B, the probability of the event B is the drone landing in the inland region. The probability of event A is 0.6. The probability of event B is 0.5. So the joint probability is the probability that both things happen. So it's this region, and we know that this region is 0.20 because it occupies 200 square meters out of 1,000 square meters, so it's 20% or 0.2. So the joint probability would be 0.2. Now, Another way of determining whether event is mutually exclusive or not is to look at the joint probability of the two events. So, if the joint probability is not 0, then the events are not mutually exclusive. So events, in order to be mutually exclusive, their joint probability must be 0. So that means that two events are mutually exclusive when one event occurs or the other, but not both. Okay, let's see examples. So, these two events are event A, let's call it, it's that the drone will land in an old region, and B, that it will land in an inland region. So the probability that the drone will land in an old region is given by these two areas, which is 0.6. The probability that will land in inland region, which is these two yellow areas, so 0.5. Now we can see here that this region, the two events intersect. So graphically, that means that so this is showing graphically that their joint probability is not 0. So if the joint probability of the two events is 0, then the intersection should be shouldn't be intersection between the two events. Okay, so here there is. So these two events, old and inland, or A and B, if we define it that way, they are not mutually exclusive. So let's see another example. Old and new. Let's call it event A is old, event B is new. You define the events the way you want. So these two events, there is no intersection. So this is old and this is new. There is no intersection. That means that the joint probability is 0, and that also means that these events are mutually exclusive. Another example, one of the events is that the drone will land in a new area, which is represented by the plain areas. And the other event is that the drone will land in an inland area. Now, again, here there is this area, the new inland area, which is the intersection, and it's covered by both events. So the joint probability is not 0, and therefore these two events are not mutually exclusive. Now, another concept is whether two events are jointly exhaustive events. Jointly exhaustive events are events that one of the two, if there are two, or if there are more of one of those, must occur. So if we know that the drone landed in the city, then it must be that it landed in the old area or in the new area. So these are jointly exhaustive because there is no other option. One of the two must have occurred in this case if the drone landed already. So jointly exhaustive events are events that one of the two, when we are talking about two, must occur. There is no other option. Let's see the following example. New and inland. So this is new, this is inland. These are not jointly exhaustive because if we know that the drone landed in the city, it may be the case that it wasn't neither new nor inland area. So because there is a possibility that one of these two events is not true, or both are not true, it means that they are not jointly exhaustive. Jointly exhaustive is that they cover all the possibilities between the events under consideration. Okay, so in the final part of the video, I'm going to explain two very important rules in probability theory: the sum rule and the product rule. Now, there are many versions of these rules. I'm going to explain one of them. Okay, so the sum rule uses this symbol, which means or. So basically, in the sum rule, we have the probability of one event, in this case old, the drone landing in an old area, or another event. So probability of old or inland, or probability of event A or event B, given the background knowledge. So basically that's the sum rule has to do with what we call a disjoint probability. Joint probability is when we use and, disjoint when we use or. And the formula is probability of old or inland is the probability of old, obviously given background knowledge, plus the probability of inland, and that's very intuitive, but this part minus probability of old and inland, and this is less intuitive. And I just remember that I didn't mention that the comma is another way of saying and. Yeah, so this is just a question of notation. Comma dividing two events means and. Okay, so what does it mean? Why do we have this? Why do we need this minus thing? It looks intuitive that probability of old or inland is the probability of old plus the probability of inland. But there is, if we use that formula, we have a problem. So, okay, so probability of old or inland graphically is the probability that the drone would land in any of these three areas. So easily we can say is 0.9, because we know this one is 0.10 is this, and is the only area excluded. Okay, so let's try by adding the probability of old plus the probability of inland. Probability of old is this area, we know is 60% or 0.6. So 0.6 plus the probability of inland. The probability of inland is half of the city is inland, half coastal, so it's 0.5. So 0.6 plus 0.5 is 1.1. We cannot have a probability greater than 1, so 1.1 doesn't make sense. Well, look at this. The reason why we get a probability larger than 1 is that we are adding this area twice. Yes, so this area we added when we consider the inland event, and when we consider the old event. So this area is added twice, so we have to subtract it once. And because this area is the joint probability of the two events, old and inland, that's the intersection is the joint probability, we have to subtract that from the rest. And it works out because we know this is 0.2 visually, and we had 1.1 minus 0.2 is 0.9. What we knew beforehand, because this is the only area not covered. So 1 minus 0.1, this is 10%, so 0.1 is 0.9. So we get to the same result graphically and numerically. Okay, now the product rule involves an extra step. So the product rule, and again, there are many versions of the rules. There are derivations, but I'm going to explain just this one. So the probability of old and inland, so basically that both things have to happen, which would be this area. And we know already that this is 0.2. So whatever we do numerically has to get us to 0.2. Okay, so the formula is probability of old times probability of inland given old. And this is a conditional probability. Now, in a sense, we are already seen conditional probabilities all the time because we always conditioned on K. So we always condition on the assumptions, the background knowledge. Yes, but now we are conditioning in something else, not just the background knowledge. We condition on that one of the events happened. Okay, so that's so technically all the probabilities that we've seen so far are conditional, but more in a practical way. We only talk about conditional probability when we condition on something else, not just the background knowledge. Okay, so let's see how this works. Okay, first of all, I return here. So we need to know these two results: probability of old and probability of inland given old. So probability of old, we know already that probability of old is 0.6 because it's these two areas, and these two areas cover 60% of the surface, so of the city, so that's 0.6. So we know that probability of old given K is 0.6, but probability of inland given old and K we don't know. So let's see how we can graphically understand what's this conditional probability. Okay, so conditional probability of inland given old. It means we have got this extra information that the drone landed in an old region. Okay, so it's not only K, that K, one of the things that K is an assumption, is the background knowledge, is that the drone will land in the city. Now we have extra information. We not only know that the drone landed in the city, we know that the drone landed in some old area. So the drone landed somewhere here, either there or there. So given that we know that it landed here in an old area, for these purposes we completely ignore the rest. So we have to delete that area, the new area. We eliminate it of this of our consideration because we know it didn't land there. Now, if we know that the drone landed in the old area, so it's here or there, now what's the probability that it was inland? Okay, so now the whole city before was 1,000 square kilometers. So our reference was 1,000 square kilometers. But now our total is not the whole city. Our total is the whole the total of the old regions. So basically that's 0.6. Yes, we know that the old regions cover 0.6. Now, of this 0.6, how much is inland? Okay, so it's the yellow area, and we can see that is 1/3 or 2/6, because this whole area is 6 out of 10, and this one is 2 out of 10, so it would be 2 out of 6. So that's 1/3 or 0.333. So the probability that the drone landed in an inland area, given that we know it landed in an old area, is 0.333. And the probability that the drone landed in the coastal area, given that we know it landed in an old area, is 0.666, which is the 1 minus 0.333. Okay, so now we can plug in the values in the product rule formula. So we knew already that probability of fault given k was 0.6, and now we know that is probability of inland given old is 0.333. That multiplication is 0.20. Obviously this is approximate because we have to just using 3 decimals here, and 0.20 is what I told you at the beginning. It was the number we need to get. So basically, using the drone delivery metaphor, we've seen events, mutually exclusive events, jointly exhaustive events, conditional probability, we've seen joint probability, and the sum and the product rules.